Hello, and welcome to Aggressive Physics. Today is day 25, where we're going to look at projectile motion at an angle. Now, so far we've discussed projectile motion when the object moves horizontally. And what was important about the horizontal motion is that there's no vertical motion to begin the problem. So for any problem that we had moving sideways only when it left the ground or was thrown, Vy is 0. So the initial velocity in the y direction was 0. Now, of course, if it's a problem near the Earth's surface, the acceleration in the x direction is typically 0. The acceleration in the y direction is typically negative 9.8 meters per second squared. That can change if we have objects that are increasing or decreasing the acceleration of gravity sideways or up and down. Maybe there's a rocket engine. Maybe there's some wind resistance that's consistent. Maybe there's some kind of other factors involved. But typically, if you have a problem where an object rolls off a side table, if it moves off a cliff at a 0-degree angle, anytime it's thrown sideways, you're going to have Viy is 0, Ax is 0, and Ay is negative 9.8 meters per second squared. Those are the three variables that will be assumed. Those are the three variables that will be hidden at the beginning of the problem. They won't be overtly stated, they will just be implied. And you need to be able to recognize that and understand that those variables are the ones you need to start with. You'll be given other information and then solve for whatever appropriate variable you're looking for. Now, if we're looking at angled projectiles, all we're going to do is take the object and have it launch at an angle. Now, when we do that, we may have a ramp set up at the end of the cliff. We may have a person throwing a baseball at an angle. We may have a person kicking a football or a soccer ball or hitting a field hockey ball at an angle. It could be someone hitting a hockey puck at an angle. It could be any time an object moves through the air with an initial velocity that is at an angle other than 0 or 90. If it's 0, it's all x direction. If it's vertical 90, it's going to be all y direction. Now, when we're given an angle and a magnitude for that angle, for example, let's say we have a vector of 50 miles per hour at 25 degrees. Well, that means the object is leaving the ground at 50 miles an hour at 25 degrees, which is the hypotenuse of a right triangle. Now, the hypotenuse does not help us with projectile motion because we need perpendicular vectors in order for this to work. What's our mantra? Perpendicular vectors are independent. So the way this is going to work is we need to force that vector into its components. We need to, what I call, break legs. Every time we see an angle, we're going to get angry and we're going to break some legs. And if we think about this sort of violent way of looking at vectors, we're going to be able to remember it. This may not be the most politically correct thing. Violence is wrong. However, with vectors, we need to coerce them to work for us instead of against us. So here's what we're going to do. We're going to take that vector with the magnitude and the angle, and we're going to find the x and y components of that hypotenuse. Well, the hypotenuse is c. If we remember from our Pythagorean theorem, we have a squared plus b squared equals c squared. In this case, it would be vx squared plus vy squared equals v squared. The v would be the 50 miles per hour. The problem is that gives us two unknowns in the equation, so we can't use the Pythagorean theorem. Instead, what we need to do is look at the trig functions. And there are two trig functions that we'll typically use in order to do this. We're going to use sine and cosine. Now, as long as the angle is with respect to the horizontal axis, meaning that it's from the ground, what we're going to be able to do is use cosine to find the x component and sine to find the y component. Now, the biggest debacle that can occur with this is if you're in radians in your calculator. So you have to make sure you're in degrees. If you're in radians, what you can end up with is a negative value. And we need to use the degree version of sine and cosine. So all I would do in this case is take 50 miles per hour, multiply it by the cosine of 25, and that would get me the x component. I would multiply 50 miles per hour times the sine of 25, and that would get me the y component. Now those components are for the velocities. So what I'll start with is VIY and VIX just from the triangle. All we're going to do is add one new step to finding the vectors and the givens list. So we start by finding the x and y velocities. Before, if it was horizontal, VIY was 0. Vx was whatever was given. In this case, we don't know either x and y because the angle means that some of that vector is in the x direction and some of that vector is in the y direction. So we need to resolve it into components first. After we do that, the problem is similar to what we've done before. AX is typically going to be 0. AY is going to be negative 9.8 meters per second squared. And what we'll be able to do is utilize other clues within the problem in order to solve for the different variables. Now what I'd like to do is show you a couple of example problems of that. Using the trig, we are able to simplify the problems and reinforce our mantra for this chapter, which is perpendicular vectors are independent. If you look at a chart of the object in motion, you'll see that the y velocities will change as the object is flying through the air. As it moves up, the y velocity will decrease because the acceleration of gravity is in the opposite direction from the motion. And on the way down, it's going to increase. It's going to become bigger in the negative direction. However, what you'll see is that each x velocity is constant. Now, let's say the problem asks for you to solve for the velocity, not x or y, at a specific time. Well, all you would need to do is find the x velocity at that time, the y velocity at that time, and that will give you two legs of a new right triangle. Now, instead of breaking them apart, we're putting them back together. And the way we do that is by using the Pythagorean theorem. If you know the two legs, you can do a squared plus b squared equals c squared to find the total velocity. But remember, velocity needs an angle. So what you'll then have to do is inverse tangent in order to find the angle. And the way that works is typically if the angle is of the horizontal again, the opposite, remember tangent is opposite over adjacent. The opposite will be Vy. The adjacent will be Vx. And you'll say tangent theta equals Vy over Vx. And if you do inverse tangent of that answer, you'll find the angle. So sometimes we need to break the legs of vectors to find the components because perpendicular vectors are independent. And other times we need to put them back together using trigonometry. So Pythagorean theorem and the trig functions will help us in this quest. Now on to some more sample problems. Now Mr. Fizz is on a skateboard that's rocket powered. And I guess the skateboard aspect is irrelevant since it's going to be in the air, but since it's on the ground at the beginning, we'll just put some wheels on the skateboard. Now, since the skateboard is rocket powered, it's going to provide a sideways acceleration of 5 meters per second squared once it's in the air. And Mr. Fizz in this case is trying to jump over a lake or a pond or something like that. He's 25 meters above the ground, and the lake or pond is 50 meters. And the question is, does he make it? Does he end up in the safe zone over here? Or does he get all wet? And what we're going to need to do is, just like we've done before, start with a givens list. And I'm going to put it up here, give myself some more room to do the calculations in a moment. We have our x, we have our y. I'll just extend that down. Now, Vx, to start, he's 15 meters per second. Vy, 0. Horizontal. Ax, which is typically 0, is going to be, in this case, our 5 meters per second squared. He still accelerates while he's in the air, in the x direction. Now, gravity is unaffected by the sideways direction because perpendicular vectors are independent, so as long as we have x's and y's separated, we're still fine. Now, ax is 5, ay is negative 9.8. That leaves us d. Now, this is the part that could be a little confusing at first because we're given dx to be 50 and we're given dy to be 25, which will be a negative because he's going to fall down. And of course, this is not to scale. That's not a very accurate cliff height. It's barely, probably a quarter of this 50. But needless to say, Mr. Fizz is quite tall. I think he's 6'4". Anyway, what I'm going to do is, does he make it? Meaning, I want to see whether or not he makes it over this bit of water. So what I'm going to actually do is not use the 50 as a givens. Instead, I'm going to calculate that and then compare it to 50. So is dx greater than 50 meters? So some problems, we're going to have extra information that will prove to be useful only at the end. In this case, if you write in all the numbers, you're going to calculate t to be different for both sides, and that would be confusing. So in this case, the 50 is actually our condition. It's our comparable number. So we're going to find dx and compare it to 50. Is it greater? If so, he's safe. If dx is less than 50, Mr. Fizz gets wet. Now, since the depth of the water doesn't really look that thick compared to him, it wouldn't be that big a deal, but I'm sure the embarrassment would be the main culprit. Now, once again, going back to the problem at hand, we're going to find t. We know more about the y direction, so dy vi yt 1/2 ayt squared. Now, one way to solve these problems, and I haven't been doing this, is instead of writing the y to the left and then just calculating all the y side, what you could do instead is use subscripts to denote the y variables. You'll notice t doesn't have a y because t is common to both. Now, what I'm going to put in is negative 25 meters equals, this term disappears, 1/2 negative 9.8 meters per second squared, t squared. You'll see a common theme with most of the y problems we do. It's 1/2 negative 9.8 t squared, and then the distance it falls. So 25 divided by 4.9, which is half of 9.8, the square root, I get 2.26. 2.26 seconds. Now on to the x direction. So dx equals vixt plus 1/2 axt squared. Normally this term disappears, but in this case it stays. 15 meters per second times 2.26 seconds plus 1/2 5 meters per second squared times 2.26 seconds squared. Now, calculating it. 15 times 2.26, that's 33.9, plus parentheses, 0.5 times 5 times 2.26 squared, close parentheses, equals, dx equals 46.67 meters. Does Mr. Fizz make it? No. He lands short, and he gets all. All right, the next problem we're going to look at is a football player kicking a ball off of a tee at a speed of 25 meters per second. Find the range and maximum height if the ball is kicked at 37 degrees and lands on the ground. Now the ball is going to go up in the air, reach a max height at half the time since this is a symmetric problem. And what we're going to do is first realize that if we see an angle, we're going to need to resolve that vector into its components. So we have 37 degrees here. We have 25 meters per second, which is the hypotenuse, and we're going to have to find Vx and Vy. Now Vx is touching the angle, so that is adjacent. Vy is opposite of the angle, so that is going to be sine. So we have cosine here, adjacent, and sine for the opposite. So the equation becomes Vx equals V cos theta, so 25 meters per second cos 37. So using the calculator, 25 times cosine 37 equals 19.97 meters per second. And then Vy equals V sine theta. So 25 meters per second sine of 37 degrees. 25 times sine 37 is 15.05 meters per second. Now those variables go into our givens list. And since this is a projectile motion problem, we're going to have a givens list that has x's and y's. The x for V is 19.97. The Vy is the 15.05 we just calculated. Ax, 0. Ay, negative 9.8 meters per second squared. Dx, unknown. Dy, since it goes up in the air and lands back on the ground, is 0. Now, we find time, use it for the x direction, and solve for dx. So let's do that now. dy equals vyt plus 1/2 ayt squared. 0 equals 15.05 meters per second t plus 1/2 negative 9.8 meters per second squared t squared. Now in this case we have two t's, so it's a little more complex. However, if we simplify it, 15.05 t minus 4.9 t squared, we'll see that every term has a t in it. So what we can do is factor a t and make it 15.05 minus 4.9 t. This allows us to solve each of these terms and set them equal to 0. So you could say t equals 0, and then the 15.05 minus 4.9 equals t equals 0. So when you do that, if you have 15.05 minus 4.9 t equals 0, we can solve for t. And t becomes, subtract the 15.05 over and divide it by 4.9. The negatives will cancel, and we're left with 3.07 seconds. Now that's the first step in doing this. And what we need to do now is take that time and use it in the x. And we'll use that in the next video because I need to... All right, the time was 3.07 seconds. So what we're going to look at now is the x direction. dx equals vxt plus 1/2 axt squared. We're looking for the range, so we're looking for dx equals 19.97 meters per second times 3.07 seconds, and then this second term cancels out. 19.97 times, still in my calculator, second answer, I get 61.34 meters. Now the problem is we also need to find the max height. Now the max height occurs in the y direction. We could do a couple of things. We could divide the time by 2 because it happens at half the time. But what I'm going to do is utilize the fact that at the top, the final velocity is 0. So I'm going to use the Vy. That stays for the initial. Ay, that stays. And then we're going to try to find the new d based on a final velocity of 0. So I'm going to use actually equation 5. Vf squared minus Vi squared equals 2AD. 0 squared minus 15.05 meters per second quantity squared equals 2 negative 9.8 meters per second squared times d. All right, so here's what we do. 15.05 squared, and that's 226. Divide it by 2 times 9.8, which is 19.6, and we'll get 11.56 meters. So that's the max height in the air. Now you may be asking, what about the negatives? Well, this negative was outside, so it stayed. This negative stayed. So when I divided the two negatives, I ended up with a positive answer. So the positive 11.6 becomes my final answer. So the range is 61, and the height, max height, was 11.56. And that's all you have to do. All right, in this problem, we have two baseball players throwing a ball to each other. And the outfielder is throwing it to the cutoff man. This is the outfielder. And this is the cutoff man. And what's going to happen is this player catches it at the same height it was thrown. So that allows us to know that the initial velocity, initial displacement and the final displacement happen to be the same. So the y direction of the displacement is 0. And what we want to find is how far apart are they, which is going to be d in the x direction. Now, first step, as always, if we see an angle, we want to resolve it into its components. So we have 43 degrees here. We have 35 meters per second. So Vx equals V cos theta. Vy equals V sine theta. So you'd plug in 35 cosine of 43 and 35 meters per second sine of 43. So those are our two equations to get the x and the y components. So 35 times cos 43 equals 25.6 for Vx, 25.6, and Vy, 35 times sine of 43, 23.87, 23.87 meters per second, and that is Vy. Now, as always, that becomes the initial velocities for our givens list. So Vx, 25.6 meters per second, Vy, 23.87 meters per second. Ax is still 0. Ay is still negative 9.8 meters per second squared. Dx is what I want to know. Dy is 0. Oh, 0 meters, not meters per second. Now I know more information about the y direction, so I'll solve for t, and then I'll use that t in the x. So let's do that. And in this case, I'll just use the y on the side to denote that I'm using the y equation. I won't use the subscripts. 0 equals 23.87 meters per second times t plus 1/2 negative 9.8 meters per second squared t squared. I'll factor out a t, so 0 equals t, 23.87 minus 4.9 t. So the two roots, t equals 0 and t equals, we'll bring the 23.87 over and divide by 4.9. We'll get 4.87 seconds. So, that being said, the 0 is not going to be useful to us because that's when the outfielder threw the ball, so it hasn't gone anywhere yet. And we'll use the 4.87. Now in the x direction, d equals VIT plus 1/2 AT squared. The a term cancels, and you're left with d equals 25.6 meters per second times 4.87 seconds. 25.6 times 4.87 gets us 124.7 meters, which is pretty far. However, that is the answer with the givens we